Yes. Okay, so we did discuss about these uh, electrode potential values for different combinations of the half cells. We did see the half cells in which these three different combinations were made. The half cell using the metal with its metal ion, half cell with non-metal with another non-metal ion, and ion with the another ion half cell. So these are different combinations which are depicting those three combinations. Okay. Now these are in detail. Half cells containing non-metals and non-metals ions. You know that non-metals include the halogen. The halogens, all of the halogens are considered to be non-metals. We have elements of the group number 6, group number 5. These are all the non-metals. In fact, one element of the group 1 is also a non-metal. Which that element is? Group 1, hydrogen. Good. Half cells. In half cells that do not contain a metal, electrical contact with the solution is made by using the platinum wire or platinum foil as an electrode. So you need to use this element for your electrode. The composition of the electrode must be made of the platinum. You have to learn this element. The redox equilibrium is established at the surface of the platinum. The platinum electrode is inert and so plays no part in the reaction. Why are we using the platinum? Because platinum is is unreactive. It is inert. So it does not take part in chemical reactions with the substances present in the half cells. In platinum, the platinum must be in contact with both the element and the aqueous solution of its ions. Figure 20.12 shows chloride half cell connected to a standard hydrogen electrode. The voltage of the Cl2 half cell is 1.36 plus 1.36. So the chlorine, if the value of the chlorine is plus 1.36, what does it represent? Will it become cathode or anode? Reduction. And which electrode will it become? Cathode. Yes, cathode. 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 How do I make it more memorable for you? Cathode, reduction, anode, oxidation. I don't have any good points to make it easier for you to remember, but I will see if I find. And then we have these equations. These equations represent the electropotential values for these nonmetals, hydrogen and chlorine. The electrode potential values show us that chlorine molecules are easy to reduce than hydrogen ions. They have a more positive E naught value. Chlorine molecules are more likely to gain electrons than hydrogen ions. So if you compare these two values, chlorine will get the electrons. So chlorine molecules will get electrons from the hydrogen. This is the representation of the half cell diagram. Hydrogen ion to hydrogen gas half cell. And hydrogen molecule will lose electron in the half cell of chlorine. The next is half cells containing ions of the same element in different oxidation states. When the same element is used but in its different oxidation states, then you get another type of the half cell. Half cells can contain two ions of different oxidation states derived from the same element. For example, a mixture of iron 3 plus and iron 2 plus ions can form a half cell using the platinum electrode. So here, what do we have? Again, we have the uh, platinum electrode used. So you have to learn the situations, the conditions in which the platinum is used. The first condition was when there were non-metals present in the half cells, and the second condition is when we are using different oxidation states of the same element. In this type of half cell, In this type of the half cell, the concentration of each ion present is 1 mole per dm cube. The figure is shown here. We have this half cell of iron 3 plus and iron 2 plus. These are the two different oxygen states. But the color, as you can see, it's a combination of two colors. Which two colors are present in this mixture? Exactly, green and dark brown. Brown, simply brown. So green and it's green brown. I can clearly see it's green brown color. No, just brown. Sometimes it is written as light brown, or sometimes as yellow brown, or just brown. I don't think so. Sorry? I don't think so. I don't know that color. Okay, I don't know about this word. So these are the colors of this solution, and here we have the different oxygen states of which element in this case? It's plus 7. Very good. So these are two oxygen states of manganese, plus 7 and plus 2. And here's the color. I think we should call it as purplish pink, pink purplish, pink purple color. Deep purple, that's not definitely deep purple. No, it's not deep purple. Pinkish purple, I will say. Using E naught values to predict cell voltages. So we have now the reduction values or reduction reactions of these two elements, silver and the zinc. E naught values and the direction of the electron flow. So the relative values these voltages thus that zinc. Okay, if you compare these two values, we have plus 0.8 volt and minus 0.76 volt. So the direction of the electron flow is from anode to cathode. From anode to cathode, which means from the uh, anode is basically the positive electrode, or is it negative electrode? Anode is negative. Anode is negatively electrode. So the electrons flow is from the negative electrode towards the positive electrode. Or in other words, we say from anode to cathode. Now looking at these two values, to cathode, anode is negative electrode, cathode is positive electrode, and this is the direction of electron flow. So from these two values, which value do you consider to be anode and which substance will become the cathode? Yes, anode. So direction of electron flow will be from zinc to silver. Zinc will lose electron and zinc is negative here. Okay. Using E naught values to predict if a reaction will occur. So this indicates the feasibility of the reaction. We have to check will the reaction will occur or not. Okay. Will iodine I2 oxidizes I2 plus ions to I3 to iron 3 plus ions? We have to check this. Okay, here we have the reduction potential value for iron 3 plus to 2 plus, and then iodine into iodide ion. We have these values. Now consider these two values. Considering these two values, which will be oxidation reaction? Which of these two will be oxidation reaction? Very good. So reduction at iron and oxidation at iodine. Now, if oxidation is occurring as iodine, is it proving this statement? Why? Okay, Fe is going to reduce and iron is going to oxidize. We are seeing that iodine should oxidize the iron, which means the iron should be reduced. But that's not the case. It is not being reduced. It is being showing oxidation. So that's the reason we say that it will not oxidize the iron 2 plus ions into iron 3 plus ion. Very good. So this reaction is not feasible. We were looking for the feasibility of the reaction. We use the word feasible. Okay. So using E naught cell values to measure the feasibility of the reactions. We have to use the value of the E naught cell to tell whether the reaction will occur or not. Uh, Basically, whenever the value of the E naught cell is positive, the reaction will always be a feasible reaction, which means the reaction should take place. Feasibility of the action means the reaction should be feasible. It should be taken place. So that is determined on the basis of the sign of the E naught cell. Now, how do we calculate the E naught cell? How do we find the value of the E naught cell? Very good. E positive minus E naught negative. What are the other names of these E positive and E negative? That is cathode. Cathode minus anode. And the other way, right hand side minus left hand side. But that is not universal formula of right hand side and left hand side. However, you can do use this one, E cathode minus E anode, or E positive minus E negative. So when you calculate E naught cell, you get some values as well as the sign of the answer. That sign will help you to determine whether the reaction is feasible or not. So we did calculate the value for the electrochemical cells formed by the zinc and copper. We got the value of plus 1.1 volt. This plus 1.1, this plus sign indicates that this reaction is feasible. Is it clear? All right. Work example. Will hydrogen peroxide reduce acidified manganate ions to Mn2 plus ions solution? We have to prove this. We have to just check this. Will this happen or not? Which means we are going to check the feasibility of the reaction. For this purpose, you must use the standard electrode potential equation for hydrogen peroxide. Hydrogen peroxide. If you check from your data section, you will find that the equation for this hydrogen peroxide reduction is this. This is the equation of hydrogen peroxide and its value is plus 0.68 volt. And the other equation it's asking about is the acidified manganate 7 ions, which means Mn of 4 to Mn2 plus ions, which means you have to select that electrode potential equation in which these two species are present in every case, MnO4 minus and Mn2 plus. However, in electrochemical series, there are multiple reactions given. You have to select the right one. So if you select the right one, then only then you will be able to answer you will be able to give the answer. Okay, here we have the values now. Now, what do you see here? We have plus 1.52 and plus 0.68. Plus 1.52 and plus 0.68. What do you suggest from here? Hmm, very good. This will become oxidation reaction and this will become the reduction reaction. Now, is this statement, what do you say about this statement? Will hydrogen peroxide reduce MnO4? Hmm? Yes, the answer is yes. Very good. So the reaction is feasible. So we say over here, so it is written here. So the reaction is feasible. Good. Now the rest is about the calculation. They are just basically finding the overall equation of these two reactions. So they are using the same rules which we discussed before, the rules to balance the rules to find the overall equation. How to find the overall equation for these two reactions, this reaction and this reaction? But before that, combining the two reactions, what is the basic necessity for the redox reactions in terms of electrons? But which thing? Exactly. Lost electrons must be equal to gained electrons, right? So how would you apply this principle on these two reactions? Very good. This reaction will be multiplied by 5 and this will be multiplied by 2, and that's how when you multiply the whole equation you get then combine the two equations and cancel out the Similar species. Okay, here's the two reactions. Uh, this is one reaction, and this is second reaction. And one more thing. When you have decided which is going the oxidation and which is going to show the reduction, you have to flip the equation. So which one will be flipped? No. Both reactions are shown in terms of the reduction, which means one of exactly the oxidation reaction will be flipped. What does flip mean here? Like over here. Exactly. The products become reactants and reactants will become the products. So we flip the equation. Also, we did multiply this equation with 5. So here we got the two equations. You can see here clearly that this is 5H2O2, which was previously the product. Now it is becoming the reactant here. Now, how would you cancel the species here? We have two reactions here. Which one will be cancelled out here? Hmm? So from these two reactions, you have to decide the overall equation. So we have cancelled out the electrons because they were present equally on both sides. What else did we have on both sides? Which other species present on both sides? Because those are cancelled. Because those are the ones which are being cancelled. Hydrogens. There are 16 hydrogen ions on the left side and 10 hydrogen ions on the right side. So it will be 6 on the left side. Very good. And the rest are just different. All of the other species are different. So that's why there is no other cancellation. But if there were any same species on same side, they will be added. If they are same species on the same side, I'm not saying on the opposite sides. If they are same species on the same side, then they will be added. If they are on the opposite sides, they will be cancelled. So here we got the overall equation of this reaction. Now I will continue from this topic onward in our next class, inshallah. Till then, take care and Allah Hafiz.